It's more of a formal kind of intuition about how the evolution behaves. I'm thinking, for instance, the mean curvature flow is the gradient flow of the area function with respect to the L2 distance, in some sense. But this is while this sentence is in some sense only formal. Okay, so everything makes sense if everything is smooth, but it's not something that there is not such a rigorous theory in some sense behind this quote. While the kind of gradient flow that we are going to study now, so today is a crash course on gradient flows, is in some sense a way better behaved situation where we will deal with functionals that are particularly nice, and we work on metric spaces. And thanks to this, we will have a quite solid concept of gradient flow. Okay, so today we do gradient flow in metric spaces. All right. All right. So what is a gradient flow? So a gradient flow trajectory in the smooth case, a gradient flow trajectory is, so if you have given a function, say on RD, or the Riemannian manifold if you wish, but let's say smooth, smooth. Well, then a curve gamma is a gradient flow trajectory, provided it solves, gamma T prime is equal typically 1 plus the minus. Of course, this is a convention. You could work with plus and change the sign to E. But from the point of view of calculus of variation, what is most natural is that a gradient flow tends to decrease the energy. Okay. Of course, if everything is smooth and you differentiate is gamma T in particular, this is the I should write this way. This is the differential of E applied to gamma T prime, which is minus. For the gamma T in particular is less or equal than 0, so the energy decreases along the flow, among other things. Okay, of course, decreases along many flows, but in particular decreases along the gradient. Okay. Now at the structural level, so what it is? So now I want to interpret this ODE in a metric setting where I don't have derivatives. And of course, how can I do so? Well, I can do so provided that I'm able to rewrite this in a way that has a metric analog. Okay. As usual, right? So we try to find a way to interpret our concepts in a weaker way so that we can generalize them. And perhaps before starting doing so, it's worth to take a moment and let's look at what it is. What are the structural elements in this ODE? Well, there's certainly a curve. This is our putative gradient flow. There's a function, certainly. And then there is this guy, the gradient. Okay. Now, if you think a moment and at what you need to define a gradient, to define a gradient, you need a metric. Okay. To define the differential, you don't need any metric. You need a smooth manifold, you have a smooth functional, you have a differential, right? But to define the gradient, you need some operation that brings the differential, which is a cotangent guy, and returns a gradient, which is a tangent guy, and this should be tangent because the derivative of a curve is a tangent object. So it's some form of metric that allows you to dualize in that sense from differential to gradients is needed. So I'm telling this because in some sense, okay, maybe in 10 years or so, somebody will come with a more general notion. But so the ingredients that we have to speak about gradient flows in a metric setting will just be functional on a metric space. Okay. Given this, maybe we can try to give a definition of gradient flow, and perhaps under some assumption, regularity assumptions on either the function or the metric space. All right. Now, let's see, how can we interpret this in a purely metric way where there is no differential structure? Well, by the way, this is all basically the geometry. It's been revisited by Ambrosio Savare and myself. And basically all of what I'm going to say is extracted from a book on gradient flows that we wrote like 15 years ago or so. And the idea is this. So let me start once again from this. And actually, let me observe the following. Say that I have an arbitrary smooth curve, and I evaluate the difference So eta is a smooth curve, and I evaluate the difference between E at eta S and E at eta T. Okay? And or perhaps okay, perhaps better this for now. And well, this is of course is the integral is equal to minus the integral from T to S of the differential of E at eta R, or perhaps eta R, I should say, applied to eta R prime, the R chain rule. Okay, now this is less or equal, of course, this is less or equal than the integral from T to S of the modulus of the differential times the speed, the normal derivative, right? And this is, of course, less or equal. Let me apply Young inequality over here. It's less or equal than 1/2 the integral from T to S of the speed squared plus the E squared at eta R. This is obviously true, right? Now, let me wonder, when is it that I have equality? So this quantity is always less or equal than this quantity. Now, when is it that I have equality? When it is that this guy is equal to this guy, say for any T and S positive, okay? And well, I need to have equality both here and here. Now, here it's easy. We have equality near if and only if, Young inequality, if and only if this number is equal to this number for almost every R, say for any R because everything is smooth. Okay. And we have equality in here if and only if basically this vector is proportional to minus the gradient of it. You see? I mean, I should realize the norm of the differential, basically. Okay? So it should point in the correct direction. Make sense? So these two together, so it's clear now that these two together, so equality, equality, if and only if eta T prime is equal to minus the gradient of E at eta T, say for any T or almost every, I mean, everything is smooth, so for everything. Okay. Now, this of course makes me happy because I have no idea how to write this on a metric space, but maybe this equality has some hope. No? This is more metric in some sense. No? There are no more vectors, but normal vectors, and then maybe this is handleable. Okay, very good. So this has been the starting point of the George's approach. So by the way, gradient flows in the metric setting are also called sometimes steepest descent curves. So in some sense, what this equality tells, but this is in some sense clear from the concept of, if you think a little bit about this equation, is that a gradient flow trajectory is a curve along which, in some sense, the functional decreases as fast as possible. Okay, provided, of course, you can always decrease it twice as fast if you double the speed, but in some sense, provided you say that the speed of your curve has to be equal to the norm of the gradient. Okay, so that fixes in some sense, how fast you can go, and with that constraint, the gradient flow trajectory is a curve for which this descent is the maximal. Okay, very well. Now let's see how can we define this concept on a metric setting. Let me start from what would be, the replacement for this guy, and the replacement for this guy is the concept of slope. So let me define. So now let E from a metric space to, well, I guess, let me say R positive plus infinity, the lower semi-continuous. Okay. Then, okay, and as usual, I consider D of E. This is the effective domain. This is the set where E is the set where E is finite. Okay, and I define the descending slope is a functional which is defined from the domain of the energy to non-negative values. And this is defined as this. The descending slope at any given point is the lim sup as y goes to x of e of x minus e of y, positive part divided by the distance between x and y. Okay, let's have a look to this formula for a moment. So what it is that this measures? Well, first of all, if E is smooth and we are on a D, then this is the modulus of the differential at x. Okay. Now, more generally, so these measures, in some sense, how fast I am able to, when it is that this is big. This is big if close to x, there are points y for with smaller value of the function, basically. So this measures how fast I can decrease my function. This is always 0 at a minimum. Perhaps this should be clear. If x is a, say, local minimum or global minimum, if you wish, then this guy is 0 because e of y is always greater or equal than x. E of x minus e of y is negative. This is the positive part. This is so z plus is the max between z and 0. Okay. So this is always non-negative. Okay. And if x is a minimum, it is 0. So for instance, for the function absolute value, this guy is 0 at the origin and 1 at any other point. Okay. Of course, you can wonder, okay, but why did you put, actually, why did the Georgi put the positive part here rather than, you know, the more natural absolute value? I mean, if I want to measure the local oscillation in some sense of a functional absolute value would be, you know, in some sense more intuitive. And the point is that, well, first of all, for gradient flows, I mean, I care only about how fast I can decrease, not how fast I can increase. So the concept I want to have in mind is, you know, the descending slope, how fast I can go down. So that's why I don't put the absolute value. And for practical reasons, if I leave you this exercise. So basically, in any case of interest, if you put the absolute value, you obtain something that is trivially plus infinity. So exercise. Let x be, say, L2 of 0, 1, if you wish, and E of f is a point of x, just the Dirichlet energy. Okay. Then the lim sup as g goes to f of E of f minus E of g absolute value divided by the distance in L2. This is identically plus infinity. Please. Yes, plus, yeah. So if, thanks. I mean, if f is in H1 plus infinity otherwise. Thanks. Okay. On the other hand, so this is quite easy. It's a little bit more complicated, but I invite you to try, as I always say. I mean, exercises are not meant to be solved, are meant to be attempted. So try. Okay. It's like if you go to the gym and your instructor tells you do 100 push-ups, and you just do 10. Well, you should do 10, right? So it's not that if you didn't do all of them, it didn't sort of help you. And on the other hand, the slope of f, well, this is equal, if you can compute, it is a part of the exercise, is the L2 norm of the Laplacian, meaning that it is plus infinity if f does not have a distribution of Laplacian in L2, perhaps squared. No, that's okay. And it is this if if f has a Laplacian in L2, then this is this. Okay. Similar exercise. Let x be say the space of probability measures on 0, 1 if you wish. 0, 1 of course does not play any role here, does not play any role here. You can pick RD and that works the same. And D, the relative entropy with respect to the Lebesgue measure. Then the lim sup, even in this case, if I do the lim sup as nu goes to nu of the entropy of mu minus the entropy of mu absolute value divided by their distance intended in the W2 sense, this is identically plus infinity. Okay. But the slope computed by this formula, actually the slope squared is the Fisher information. So this is equal to sometimes it is called I of mu, the Fisher information, which is the integral of grad rho squared over rho. Okay, if mu is equal to rho Lebesgue plus infinity otherwise. In fact, the hard part of these exercises, which is this identity and this identity, we shall see actually during the course of my lectures, I will solve this. But meanwhile, try. Okay. All right. So at least this should convince you that you don't have to put the absolute value does not work. Okay? But the slope does. And now, okay, now I've told you who is the replacement for this guy. Now, who is the replacement for this guy? And this is the concept of metric speed. So let me give a definition. So a curve gamma, say defined on 0, 1, with value on x, metric space is absolutely continuous. If there exists a function f, say in L1, such that the distance between gamma t and gamma s is bounded from above by the integral from t to s of f for any, say, t less than s, t and s in 0, 1. All right. If x is R, this boils down to the usual, definition of absolutely continuous function. Say from R to R. Okay, but written in this way makes sense for an arbitrary curve. Okay. Now, absolutely continuous functions are those that are different. They are A, differentiable almost everywhere, and B, they are the integral of their derivative, basically. So they are, in a sense, a good starting point for taking derivatives. And this is the same for the level of curves because of the following proposition. So let gamma be absolutely continuous. Then, first of all, the limit as h goes to 0 of distance between gamma t plus h and gamma t divided by h, let me call it gamma t prime, this exists for almost everything. Let me see, 1. 2, this guy is in L1 of 0, 1 of the domain of definition of gamma. And 3, it is the list L1 function that can be put here. Yeah, here. List in the almost everywhere sense. In the L1 almost everywhere sense. That is to say that if for any function f that you can put in here, this metric speed is less or equal than f almost everywhere. I mean, that's the best you can hope for L1 functions. Okay. So we are like the 8th lecture, I guess. This is the first derivative that we pick. It was about time. Okay. So let's prove this lemma, this proposition. It's not hard. And how do you prove it? Well, you pick, say, a sequence xn, dense. Okay, don't remember. Okay, then say in gamma of the unit interval. If a curve is absolutely, so I mean, I didn't assume the space to be separable, so I forgot, but that's not too bad, because so if gamma is absolutely continuous, certainly is continuous. So the image of the interval is certainly a compact set, and therefore is separable. Pick a countable dense set in that separable guy, and consider the following functions. The n of t is nothing but the distance between gamma t and xn. Post-compose the curve with distance from xn. Now, it is clear that the distance, or it should be clear, that the distance between gamma t and gamma s is equal to the sup in n of the distance of dn, I guess, s minus dnt, every t less than s. Is it clear? So distance function is one Lipschitz. So this inequality is obvious, right? It's triangle inequality, if you wish. For this other inequality, you just use the density, right? You pick xn to be very close to, I mean, one of the two guys. I don't remember. If close to one, you get the distance. With the other one is minus the distance. Okay. Very well. Now, because of this, in particular, for any n, this quantity is bounded from above by this quantity, which is in turn bounded from above by the integral from t to s of f. Right? So this function, so t to d and t, is absolutely continuous. I mean, this is a real valued function. This is absolutely continuous in the classical. Makes sense? With derivative almost everywhere. Make sense? Right? Because the dns minus dnt is less or equal than d gamma t gamma s, which is less or equal than the integral from t to s. Right? So this will. Now I define G to be the sup in n of dn prime. G is a function well defined almost everywhere, and inner one, right? So G, of course, G is less or equal than F. Okay. Perhaps I mean this. Okay. And so G is inner one. Okay. Now, okay. Now I claim that the metric speed is equal to G. Okay. And if I do so, I've done, because I would have proved that this is inner one, because G is inner one. And I also, given that G is clearly less or equal than F, the metric speed would be less or equal than any F, that you could put on the right hand side. Okay. Well, but how much is it, the lim sup of, as h goes to 0 of the distance gamma t plus h gamma t divided by h? Well, this is less or equal. Actually, this is equal to the lim sup in h of the sup in n of dn t plus h minus dn of t divided by h. Right? Because of this equality, I just, for any t and h, I just replaced the distance between the gamma t and gamma t plus h with the sup. Okay. But now dn is an absolutely continuous function, so this is equal to the lim sup in h of the sup in n of the integral from the average integral from t to t plus h of the derivative. Right? And I can certainly bring the sup inside, and this is less or equal. So the lim sup h of the average integral of G. Right? Make sense? Okay. But this is equal, G is in N1, so this is equal by Lebesgue theorem. This is equal to G almost everywhere. So the lim sup of this difference quotient is bounded from rho by G almost everywhere. This is not easy, so don't get scared if you don't succeed. What about the limit? The limit as h goes to 0 of the same quantity, b gamma t plus h gamma t divided by h. Well, for any n, this is greater or equal than the limit over h of the distance, the n, t plus h, the n t. All right. But this, of course, is greater or equal. Actually, I can also do so like this. Just take one limit from one side. I mean, this is actually no. Wait a second. Yes, this is true for almost everything because of the differentiability points of this function is absolutely continuous, so it is almost everywhere differentiable. So this limit is actually a limit for almost everything. Let me put it this way, and this is equal to I guess the no, wait a second, I'm in trouble. Oh, yes, this okay. And this is equal to dm prime at t for almost everything. You agree? This function is absolutely continuous. The absolute value I can take it outside, right? And but this was true for every n, and so I take the sup in n and I end the proof. Make sense? Okay. So I just use this one Lipschitz function to basically reduce the problem to a problem in R, where I know the derivatives exist, and then I take just the sup. This is a rather common procedure in non-smooth analysis. Okay. All right. What is what I want to say? Yes. I have another exercise. So this quantity is called metric speed. Sometimes in some application, one wants to deal with curves, say, with constant speed, say unit speed. Okay. In this case, it is good to know that you can always reparameterize an absolutely continuous curve in order to get a curve with basically the same image but constant speed. Okay. And this is something that in the smooth setting you all know how to do. And in fact, in some sense, the construction can be pushed up to this level of generality. I leave you as an exercise the formula. In some sense, getting the formula is more than half of the job in this case. So let, say, gamma be absolutely continuous. And define, and then define, say, a function, let me call capital T. Capital T goes from, is defined on an interval whose length is this. This is what we certainly want to call length of the curve. Okay, so it's defined on the interval, long as the length of the curve to 0, 1. This is my reparameterization function in some sense, and T of S is defined as the inf among all t's, or maybe 0, 1, such that the integral from 0 to t of gamma prime r dr is greater or equal than s. Okay. this is our reparameterization function, and then define eta of S. Now, eta is a curve defined on this interval. And eta of S is defined as gamma at T of S. Okay? I gave you the definition of eta, and the exercise asks you to prove that eta is absolutely continuous. Okay, defined not on 0, 1, but and with metric speed identically equal to 1. Okay, with same image. Okay, with same image of gamma. Okay. Here, the bordering technical issue is that this function capital T in general is maybe not continuous. Imagine what happens if you have your curve gamma that starts, moves, then stands here for a little bit, and then moves again. Okay, when you want to reparameterize this curve with constant speed, you want to follow and then, in some sense, forget about this interval of time where the curve was standing still and just move forward. So that's why the reparameterization map has to be defined in this way. It might be not continuous, but still the resulting curve is absolutely continuous and with metric speed exactly equal to 1. Okay. All right. Okay. Now we are almost able to define gradient flows or gradient flow trajectories, but before doing, in fact, the terminology that I just introduced would be sufficient. But in fact, we will not work with general lower semi-continuous functionals. We will work with convex functionals or geodesically convex functions. These are a way better class of functional, way better behaved, and for which, in particular, the theory of gradient flows works particularly well. So I won't dig at all into the more general theory. We'll just focus on the case of k-convex functionals. So I will write the definition, and I'm sure this will look familiar to you. So let's say say that E is a function from x to say r positive plus infinity, lower semi-continuous. We say that E is k-convex or k-geodesically convex, but let me drop the geodesic term. K is a real parameter. If for any x0, x1 in the domain of the energy, there exists a geodesic from x0 to x1, such that the energy at gamma t is less or equal than 1 minus t energy at gamma 0 plus t energy at gamma 1. And I will stop here if we were speaking about convexity. If I speak about k convexity, I have to add correction, which is this. Right? For everything. So, of course, you see that this definition is basically the same that we used for the loss through Milanese condition, right? So the space CD k infinity if and only if the entropy is k convex in this sense, in this space of probability measures, right? And of course, if I read this definition on RD, say with k equals 0, I get back to the classical concept of convexity, where segments, are interpreted as geodesic, or geodesics are segments. Right? Now, if you have a little bit of familiarity with convex analysis, you know that, and perhaps you, or if you don't, you might have heard something when I introduced the concept of C concavity and C superdifferential. So in convex analysis, there is this magical fact that you can speak about differentials without taking derivatives, or if you wish, the differential operator as a global interpretation. No? Recall, perhaps. Let me open a parenthesis, recall. If, say, E from RD to R is convex, let me say convex smooth, just to, I mean, smooth is totally irrelevant, but let me just, then you know, V is the gradient of E. Perhaps I should correct. The W is the differential of E at X if and only if E of X plus W applied to Y minus X is less or equal than E of Y for every Y. Right? So what in principle should be something that holds when Y goes to X, thanks to the convexity in you know, assumption, becomes something global. Okay, and that of course is beautiful because you know, among other things, I mean, shows that the differential for convex function is a much more stable notion. Because you can start from this and prove that if a sequence of convex function is converging pointwise, then subdifferentials also basically converge pointwise, kind of. Please. Smooth. Sorry. Okay. Now it is easy to see, now this was just that's motivational, but it is easy to see that if E is K convex, then the slope that I previously defined, did I erase it? Possibly. Yes. Okay. Well, then, anyway, then the slope is actually equal. So this was, so the lim sup as Y goes to X. So I rewrite it. E of X minus E of Y, positive part divided by the distance between X and Y. This was the slope. Right? Well, this is actually equal to the sup over all Y, not X, of EX minus EY divided by the distance plus K over 2 distance X, Y. So it admits an interpretation as supremum rather than lim sup. In some sense, you know, hope you see the analogy with this above. Okay. I will prove this in a second, but let me just point out that, of course, this is way weaker than this, because the slope is basically a number, while the differential is a vector, or a vector if you wish. So it's a sub-differential carries many more informations. But still, you know, it's a sort of first think in that direction. So let me prove this. Of course, this is obvious, because if you take the lim sup when Y goes to S, this will not just play any role, right? And so instead, the lim sup of this quantity when Y goes to X is the same as the lim sup of this quantity, because this becomes small. And of course, the lim sup is less or equal than the sup. Okay, so I have just to prove the other inequality. Given that I'm a bit lazy, I will do this for K equals 0, but you know, you will see that you will see that generalizes to general K, I mean, in a moment. So what I have to prove, if I want to show this other inequality, well, I have to prove that for any Y, I can find a sequence of points for which this difference quotient, say, sequence of points going to X, so the difference quotient is bounded from above by this ratio. Make sense? Okay, and which points will I pick? Well, I will pick the geodesic along which that inequality is satisfied. Right? You pick. So let me just, you know, I start from, you know, my function is convex, say K equals 0. I start from that inequality, and what I conclude, I mean, just with manipulation, I get that E of, say, gamma 0 minus E of gamma 1 divided by the distance gamma 0, gamma 1, this is less or equal Let me see. Then E gamma 0 minus E gamma t divided t times the distance between gamma 0 gamma 1. I just, forget about the last term. I just sort of rewritten things and divided by t times distance gamma 0 gamma 1. Okay. Now, gamma was a geodesic between gamma 0 and gamma 1. So by a definition or a consequence of the definition, this is the same as the distance between gamma 0 and gamma t. Geodesics for me have constant speed. Right? But then you see, this is fixed. This is true for any t. So this is particular is also less trivial than the lim sup. T, say, goes to 0. But of course, this quantity is less Origo than the slope of E at gamma 0. Because these gamma t's are just, one family of points going to gamma 0. Make sense? Right? And here, I had arbitrary point x naught, x. Okay. All right, maybe this is a good moment to take a small break, 5 minutes, and then we see how, starting from this formula, this global version of the slope, we can quick.
I know, but I feel like a month goes like
especially when you're doing other things.
Yeah, exactly.
All right. How's it going? Questions? A lot, maybe. Been a bit fast. Well, if there are no questions, let me perhaps move on. So if you recall, the motivation, the initial motivation I gave for attempting a definition of gradient flow in the metric setting was based on the inequality like this. Well, okay. After a little bit of manipulation, I mean, this was in the smooth setting. I wrote this inequality, right? Among other things, and then I used Young inequality. But first of all, I used this inequality. Now, this inequality I could have, written this because the object here were smooth. Okay, of course, you should not expect an inequality of this form to be true for arbitrary functionals and arbitrary curves. Okay, for instance, say that we move to the metric setting, we replace this guy with the slope. Okay, this guy is a metric split, and I wonder whether for any, I don't know, lower semi-continuous functions, it is true that I can bound the difference of the energy by this integral along any curve. Okay, and the answer is clearly no. Clearly no, because what you, in some sense, in order for this to be true, you need some absolute continuity of the function, right? So you can easily find counterexamples by, take a function that makes a jump. The slope is 0 everywhere, literally at every point. Okay, but of course there is no way that you can bound the difference, of the function at different points by integrating the slope multiplied by some, parameter split. Okay, there's no way. But if the function is convex, this works. Okay, and this is a crucial regularity property of convex functions. And the dilemma, if you wish, the key lemma that will justify our definition of gradient flows is the following. So let E be, say, K convex and lower semi-continuous, and let's say gamma be absolutely continuous with image in the domain of the entropy and the energy. Okay, takes value where the energy is finite. Then I can bound the energy at gamma t and the energy at gamma s via the integral from t to s of the speed times the slope for every, say, t less than s. Okay. I notice that I'm not stating that this quantity is in L1. It can be plus infinity, and of course, if the integral is plus infinity, I'm only happy because it's certainly greater or equal than the left-hand side. However, if this function is L1, then I can bound the difference. Lower semi-continuous, I assume, of what? Sorry.
Your definition assumes open.
Ah, yes, you're right. Okay, yes, of course. So nobody ever cares about convex functions that are not lower semi-continuous. That's the truth, right? In some sense, for the same reason that nobody ever cares of linear functions that are not continuous. Yes, yes, absolutely, absolutely. But I have to say, in the proof, actually, some things like this identity that I wrote here is true even if I don't assume lower semi-continuity. In any case, I will always. But even if I don't, this inequality is true. But I don't know if this is true if I remove lower semi-continuity. In fact, I'm afraid it's false. But so the proof I know works with lower semi-continuity. Okay. Okay, let's prove it. First of all, I will skip some detail, but I want to, in some sense, convince you about the fact that this is true. So first of all, I can assume, by reparameterization, can assume that the speed of gamma is 1. Use the reparameterization argument, and notice that, in some sense, by the chain rule in 1D. In some sense, so these inequalities invariant under reparameterization. That's, I think, what I want to say. Okay, so I reparameterize by constant speed via the exercise that I gave before, and I fall in that case. Okay, another thing is that it is sufficient to prove. So what I really want to prove is that that if, well, okay, I guess the map that takes t and returns the slope of E at gamma t is in L1, then the derivative, then t to E gamma t is absolutely continuous. I mean, if I prove this, I'm done. That's I guess what I want to say. Gamma is speed 1, so that's why there is no gamma dot in this. Okay, and let's say that I've proved this. Then I guess once I've shown that this is absolutely continuous, I know that it is differentiable. This is a map from R to R. Okay? So I know that it is the integral of its derivative. So I know that E gamma t minus E gamma s is equal to the integral of the derivative. But now the derivative, it's clear that if E, what is gamma t plus h minus E gamma t divided by h. Actually, let me do the like this. Let me do the limit. Let me say when h goes to 0 from below. So the h here is negative, and basically I can write this in this way. This, of course, is less or equal than the limit when h goes to 0 from below. And now you see, let me multiply and divide by the distance between gamma t and gamma t plus h. Okay, and what I get is, well, let me say, so E gamma t minus e. Perhaps let me take some space. Let me write it here. So e, what is this? dt e gamma t is equal to the lim when h goes to 0 of that difference quotient, which is less or equal than the limit when h goes to 0 from below of e gamma t minus e gamma t plus h divided by the distance times the distance. I mean, it's what is the chain rule, the usual thing, right? Okay. And of course, this inequality gets only stronger if I take the positive part of the right-hand side. And the only thing that possibly had the wrong sign was this. But now this is bounded from above. This goes to the speed, which is actually 1, by the way, by the repatternization. And this goes, is bounded from above by the slope of E gamma. You see? So the only thing that I need to prove is the regularity property of this function, of course. Okay. But that I can do because I can reduce the problem to a problem, in real analysis. What I do is I define now the function f of t and g of t. Now, f of t is just the energy gamma t, and g of t is the sup over s different from t of f of t minus f of s divided by s minus t. Right? Now notice that, again, my goal is to prove that f is absolutely continuous. This g of t is, okay, this is less or equal. I mean, notice, so s minus, given that my curve has constant speed 1, the distance between gamma t and gamma s is bounded by s minus t. Right? And so this ratio is less or equal than the sup over s different from t of e. Let me take positive. Well, actually, e gamma t minus e gamma s divided by the distance between gamma t and gamma s. Right? And but if you recall this formula, the global formula for the slope, and you notice that gamma being absolutely continuous as a bounded image, so this quantity over here is bounded by some number. This is less or equal than the slope at gamma t plus some constant. Make sense? Thanks to this global version of it. Okay. So now we have an exercise in real analysis. The exercise is, so let f be from 0, 1 into r be such that lower semi-continuous. It's lower semi-continuous because it's the composition of a continuous curve with a lower semi-continuous function. So it is lower semi-continuous. And put, define G, G as in here. There's no E, there's no gamma. This is a function G that's defined from F. And assume that G is inner 1. Because if this guy is inner 1, this bounds from above G. Okay. Or perhaps let me take a positive part so that we don't, G is not negative, so bounded from above is sufficient. Okay? Prove that f is absolutely continuous. I really have a function on the interval, lower semi-continuous. I define this guy and prove that that is actually absolutely continuous. Okay. There are no metric spaces now. All right. So if you don't prove it, well, believe me that this is true. So in some sense, the conclusion of our lemma holds. So this means that in the case of convex functions or k-convex functions, we really have this bound. We really can bound the difference of energy in with the integral, with that integral. Okay. So we can define so definition. So let E be k-convex and lower semi-continuous, or well, k-convex. I can't have to write and lower semi-continuous. And we say that, say, a curve gamma, typically defined on a half line, but you can easily modify the definition to let it be a bounded interval, is a gradient flow trajectory if the energy, well, first of all, if the energy of gamma t actually, well, gamma is finite for every t, and the energy at gamma t is equal to the energy at gamma s plus 1/2 the integral from t to s of gamma dot r squared plus the slope of it squared gamma r dr for every t. Okay. Okay. You can view that lemma as a moral justification that this definition makes sense. In some sense, it's carrying really information. Okay, because this inequality is always true. Actually, I should say, if perhaps I should specify, if it is absolutely continuous, it is absolutely continuous, so that this makes sense. Okay, so this inequality is always true. So the content of the definition is this inequality, right? That tells that when you move forward in time, s is bigger than t, you should decrease the function, right? And you should decrease as much as you can because of at least this quantity. Typically, you cannot stand still because if you stand still, unless you are at a minimum, this guy will be positive, and this guy will be 0. But then the energy will be constant, and so you have this inequality, but not this. Make sense? What I'm saying? And notice also that it is sufficient to ask, sufficient to check. Because this is true always, sufficient to check the case. T equals 0 and NES. Right? Makes sense? Huh? This is should be, I mean, if you think about it for one moment, this should be clear because you have, suppose that you know that this is true from t equals 0 and a certain s, and pick an intermediate time t. Right? Then I mean, since the dissipation is additive, there's a sort of a telescopic kind of thing that is going on. No? The dissipation from 0 to S is the sum of the dissipation from 0 to T plus that from T to S. No? And okay, so you have sort of, by the validity of this, for any point, if you have the other inequality from 0 to S, you are forced at equality for all intermediate couples. Okay. In some applications, I mean, you can, I mean, the literature here, I mean, this, I mean, diverges a little bit. So for sure, you want the energy to be finite at positive T's, because otherwise you cannot be a gradient flow trajectory if at least your energy is not finite. One can discuss whether imposing the energy to be finite at time 0. Often one does not force this, but in this setting, in a sense, this is a quite natural requirement, meaning that there are no existence or any kind of result if you don't also ask T that at T equals 0, the energy is finite, basically. Okay, now that's the definition. Of course, it's easy to draw definitions. The hard part is to attach theorem to that definition. And in particular, I mean, we have just a convex function on a metric space. So this definition, do we have gradient flows? Yes or not? I mean, that's the first question. Do we have existence or not? Now, luckily for me, even though this question is conceptually very, very relevant, I actually don't need to know the answer to this question for the purpose of my talk, of my series of lectures. So I can be satisfied. I give you the theorem, but I will not prove it. And the theorem is this. And this is basically the logic. Okay. Let X be compact. Perhaps the Giorgi plus, let me say. E K convex. And lower semi-continuous. Say X is a point in the domain of the energy. Then there exists a gradient flow trajectories starting from X. Gamma with gamma not equal X. Okay, there are. Okay. This compactness assumption can be actually, I mean, or let me just say, or sublevels of E are, you know, intersected bolts compact. I mean, that's bolts, closed bolts. This, the Giorgi's proof works equally well in this case, but which does not add that much of a generality in some sense. Okay. I will not prove this theorem. I will just tell you the basic idea of the proof. Well, or actually not the basic, the first step, let me say. And the first step is this, is to realize, let's go back once again to the smooth case. And how do you prove existence of gradient flows in smooth case? Of course, if you are on RD and the function E is smooth, then the gradient is a smooth vector field. You can apply Cauchy-Lipschitz theory. Okay, but even if already you are in RD or maybe on a Hilbert space and your function is only convex, then convexity is not sufficient. I mean, convexity does not imply Lipschitz regularity of vector field. It only implies a certain kind of monotonicity. And existence is typically obtained in the following way. So by basically solve what is called the implicit Euler scheme. The idea is to say you fix a time parameter tau bigger than 0, and you basically you want to solve a time discretization of the gradient flow equation. Say that we are on RD and define and recursively define say X tau 0 is our initial point X. And if you define X tau n, you define X tau n plus 1 such that the differential of E at x to n plus 1, actually the gradient, let me see, this should be equal to, okay, I have to pay attention, a little bit of attention to the sign. Let me think 1 second. N, actually n plus 1, x to n divided by 2 to the minus. So suppose you're able to find x to n plus 1 such that this is true. Yes. Then what you can do is, okay, I start from my point x, I define x to 0, and then x to 1, x to 2, x to 3, etc., etc. And this equation is a discretization of, this is almost, this is kind of like x prime equal minus grad E, right? This is sort of discretization in time of this equation. So you can hope that you iterate. You pass to go to 0 by some compactness, you get some limit, and then the limit is a gradient flow. Okay. Now, of course, I mean, I moved with this case the problem from solving this equation to first solving this. So I should show that this is solvable, and then improving that the limit satisfies it. But now the interesting thing is that this is basically easily solvable in many circumstances because of the variational nature. So just minimize the energy plus, well, let me write directly in the metric way, distance from the previous point divided by 2. If you are saying RD, the minimizer, any minimizer of this function, which should exist by some, minimal compactness argument, satisfies this. Okay. And the starting point of the George's proof is, of course, well, I can minimize this even in metric spaces. And maybe, this sort of scheme can be run even in that context. Of course, in metric setting, proving that the limit is actually a gradient flow trajectory is much harder, and I will not prove this, but that's the starting point. Okay. Other things. I will not prove this because luckily for me, I will not do this result. I have existence, but then the second question is, what about uniqueness? In particular, maybe you are familiar with the fact that on RD, or homogeneous Riemannian manifolds, the gradient flow of a convex function contracts distances. How many of you have never heard about this, by the way? Gradient flow of convex function contracts distance. Okay, very well. So let me put out this. Say that we are, again, on RD, if you wish. E and E is a smooth convex. Let's say that I have two curves solving this equation. So two gradient flow trajectories. Well, let me first of all perhaps observe one crucial thing, one crucial property of the subdifferential. So let me pick, let me just for brevity, let me put V equal grad E at X, W equal grad E at Y. So I have this inequality that is true because V is the gradient of the energy at X. I also have the other inequality, the energy at Y plus W dot X minus Y is less or equal than E of X. Right? If you add these two inequalities up, the energy will disappear, when they simplify, and you remain with the bound, which is what is X minus Y scalar product V minus W is greater or equal than 0. Okay. And with that at end, let's compute the derivative of the distance between gamma t and eta t, distance squared. Well, everything is smooth. I can apply, Leibniz, whatever. This is gamma t minus eta t, gamma t prime minus eta t prime. I use my equation. This is equal to minus gamma t eta t, and then I have grad E gamma t minus grad E eta t. But this is a sign. Okay, so this is less or equal than 0 for convex functions. Okay, so in particular, gradient flow trajectories are unique, because if I have two guys that start from the same point, they must continue to be the same. Okay, and more generally, if you play this trick with k convex, yeah, I mean, actually, what this tells that the distance between gamma t and I mean, this is stronger than uniqueness. This just tells you an estimate. Tells you that the flow contracts distances. You start from any 2 points, any 2 gradient flows trajectories. They must be closer than the initial points. If you don't have a convex function but a k convex, this is perturbed by an exponential factor e to the minus kt. Okay, so in particular, if k is negative, distances can increase. Okay, but still, uniqueness is still there. Okay. Now, this argument, in order to prove this, we needed to differentiate the distance squared and to use the fact that this derivative is given by a scalar product. So this kind of thing is very Riemannian-like and not very Fisher-like. In fact, there are counterexamples to uniqueness if you move away from the Riemannian setting. So in general, example, take a symmetric space, take just R2 with the L infinity distance. And define a function E, E of x1, x2 to be just x1. You can check that this function is convex with k equals 0. Notice that in order to state so, it is important that in the definition of k convexity, I said for any couple of points, there exists one geodesic along which the function is convex, not along every geodesic. Okay, because in R2 with the L infinity norm, there are given that the norm is partially flat, there are many curves that are geodesic. So, for instance, this curve is a geodesic, but of course the function on this curve oscillates back and forth, and so cannot be convex. Right? But whenever I interpolate with segments, these are geodesics, and convexity is true because actually the functions are fine. Okay. Okay. Now it is an exercise to check that the slope of this guy is identically 1. What else can it be? This is just the first coordinate. Okay. And now let's wonder what the gradient flow trajectory is starting, let's say, from the origin. And okay, a gradient flow should be something that tries to decrease the function as fast as it can. So a first conjecture about the gradient flow, I start from here and I move to the left with speed 1. And I can check that this curve satisfies the inequality that actually I just erased. So this confirms the George's theorem in R2, of course. Perhaps that was not the point of the example. The point is that even this curve, or this curve, or anything that moves to the left with speed 1 and up and down with speed less than 1 is still a gradient flow trajectory, because the value of the function at time t is always minus t, and the speed is always 1 because the vertical part of the speed does not matter as long as it's smaller than the horizontal part. Okay, so uniqueness dramatically fails if you don't have Riemannianity. Okay, of course you can say, well, I mean, this is not a strictly convex function, and the norm is not strictly convex. No? Maybe as soon as you have theorem, you have a Banach space, or actually RD with a norm, strictly convex, and a strictly convex function, then maybe gradient flows are unique. Nobody knows. Okay, so that's, you know, situation gets, you know, as hard as this. Okay, so there's no uniqueness result. Okay, there is one particular case which is relevant and whose proof I would have loved to give you, but I think I will not have time, so we just take. So theorem, and this is a theorem of mine. This is the, I guess, the first result about heat flows on metric measure spaces. I mean, in the sense of loss to Milanese. Let's say a normalized. Let mu be in the domain of the relative entropy. Okay, then the gradient flow, well, there is at most one gradient. Then there is at most one gradient flow trajectory starting from you. Okay. In this case, regardless of any kind of Riemannianity assumption, uniqueness is still restored. This is the only result about uniqueness of gradient flows in a non-Riemann-like setting that I know. There's quite of a coincidence that this. Okay, I don't have any deep explanation as to why this is true. Let me just give you one idea of the proof. Because it is the first time, and we'll see many instances of this phenomenon during this series of lectures, where the horizontal geometry given by the optimal transport problem interacts with the vertical geometry, in some sense given by standard affine interpolation. And the key lemma, that I will not prove, but the key lemma states that the map that takes mu and returns the slope of the entropy squared. This map is well defined on the domain of the entropy. This map is convex. Convex with respect to affine interpolation, not geodesically convex. The K convexity of the relative entropy allows to conclude this convexity, K is lost here, just convexity, of this guy. Okay? If you have this, then the conclusion is easy. Because if you have this, and I will not prove that lemma, but if you have that, one can conclude as follows. Say that mu t and mu t are two gradient flow trajectories, starting from the same mu zero, and consider the curve sigma t. Just take the average. Okay. Notice that how much is it the distance squared between, say, sigma t and sigma s? The optimal transport problem, if you think about this, you can pick an optimal map, an optimal plan, sorry, from mu t to mu s, and another optimal plan, say gamma 1, no? Say gamma 1 is optimal, or gamma, say, is optimal from, or gamma is a bad word. Alpha is optimal from mu t to mu s, and beta is optimal from mu t to mu s. if you take their average, alpha plus beta divided by 2, this is, at least is an admissible pram from sigma t to sigma s. Right? So I can use this plan to bound from above this guy. Okay? But then integrating the cost, integrating distance squared, is linear at the level of plans. So this is less or equal than 1/2 W2 squared mu t mu s plus W2 squared mu t mu s. Just because, this is not visible, maybe not optimal. Okay? Out of these, you can deduce that given that mu t and mu t were absolutely continuous, also sigma t is absolutely continuous, with the derivative, the metric derivative being, so if you want the metric derivative, the squared metric derivative is convex. The squared Wasserstein derivative is convex for almost everything. Okay. Okay, but then we have that the entropy of mu 0 is on one side it is equal to the entropy of mu, say, capital T plus 1/2 the interval from 0 to capital T of mu t dot squared plus the slope right for any t, right? And the same for nu. This is the fact that nu is a gradient flow trajectory, right? But now, what's the point? The point is that if these two are different, are not the same, then there will be some capital T such that mu capital T is different from nu capital T. Okay? Pick that T. You write this identity for mu and this identity for nu, and then you take the average. Okay? When you take the average, of course, at the left-hand side, you still have the entropy of mu 0. And here you have equality of entropy. The average of the entropy is mu capital T plus, you see where this is going, no? Right? Divided by 2. And then you have plus 1/2 the average, 1/2 of this term of the 1/2. But this squared slope is convex by this lemma that I mentioned. The speed is convex by trivial reasons. So this is greater or equal than, you see, I can put here speed squared plus slope squared. And the contradiction comes from the fact that the entropy is strictly convex. Rho log rho is a strictly convex function with respect to affine interpolation. So if these two guys are different, the entropy of the midpoint will be strictly smaller. Right? But this is impossible so that will contradict the inequality that is always true for gradient flows, right? You cannot have that the energy at time 0 is strictly bigger than the energy at the later time plus 1/2 this guy, because the entropy is convex. Okay? So you have this interaction of the Barstein geometry and these this affine interpolation that plays a role. Okay. All right. Let me conclude with a couple of words about stability. By the way, if you combine the George's theorem with this uniqueness result, now at least if the base space XDM, if X is compact, then the space of probability measures with this W2 distance is also compact. So the George's ensures existence. This result ensures uniqueness. And if you believe to Jordan, Kinder, and Otto, we can say that this gradient flow that we now found is the heat flow on these CD infinity spaces. Okay. Now, of course, you can be a little bit suspicious because typically heat flow is something where you have something of this form, right? So you should at least to speak about the heat flow, and I promise we will have in few lectures. Okay. As of now, if you have no experience with optimal transport and JKO, this is totally invisible, almost unbelievable. I wouldn't believe, but I promise that there is a come. Okay, so the evolution of the densities in here will satisfy this equation. So we will actually have PDs in this metric measure context. Okay. Stability. Now, so first a remark. So of course, gradient flows are, the equation of gradient flow is a first order equation. You cannot expect solution to this equation to be stable under a zeroth order convergence. No? So for instance, you can have a sequence of functions. It's easy to build sequence of functions, say on R, converging uniformly to a limit function, but for which gradient flows don't converge to gradient. For instance, just take, En is just like this with a little bump, smooth, but the bump is always, smaller, and then the limit is just this guy. So you see that in the limit function, if you start from a gradient flow, you move to the right and you decrease the energy. But at any n, given that there is a local minima, you cannot surpass the local minima with the gradient flow trajectory. There. Make sense what I'm saying? So at the approximated level, all the gradient flow trajectories stop here because there was a bump, but the bump disappears in the limit. So in the limit, I just continue. Make sense? So you cannot expect, for instance, uniform convergence to imply convergence of gradient flows. Okay, of course, the first order equation you cannot. However, as I already mentioned before with the convexity business, if the functions are uniformly convex or uniformly semi-convex, then I have a uniform second order bound, and then maybe I can pass the limit. Okay, and the theorem is this. Theorem. This is also a theorem of mine on the same paper as before, but see also Sandier Serfati. That's 1.8. The theorem does the following. So say that En are a sequence of functions on the same. Let me call it y to 0 plus infinity. Be k convex and lower semi-continuous. And so that En gamma converges to infinity. Let say gamma nt be a gradient flow trajectory for En. Okay. With gamma n times 0, which is converging to a limit point, x infinity, I guess, and is a recovery sequence, meaning that the energy infinity of x infinity, if you want, is greater or equal than the limit sub in n of the energy n of gamma n0. The other inequality is always true by gamma convergence. So this is, I'm asking that the energies converge. Okay. And this is finite. Okay. Then, well, actually, so these are the hypotheses. I hope this is clear, does not confuse your brain. Then two things are true. First of all, there is compactness. Namely, this family of curves is pre-compact in the topology of with respect to local uniform convergence. Any subsequence as a further extraction such that on any compact interval of 0 plus infinity, it converges uniformly to a limit curve. 2, any limit curve is a gradient flow trajectory for infinity, starting from x infinity. Okay, the proof of this is easy. I will outline it in a second, but before going to the proof, let me point out why this is relevant for our purposes. So if you believe me that the gradient flow given by this result and the George's theorem is the heat flow, now you can interpret this as saying, okay, perhaps under some compactness assumptions at least, the heat flow of CDK infinity spaces is stable. Okay. And the stability of the heat flow will be, the cornerstone of all the stability results for differentiation operators in this CDK infinity setting. Okay. If you believe that the heat flow, yes, is the solves dt rho equal Laplacian of rho. So in some sense, the Laplacians will also pass to the limit. Please.
Plus infinity on the left-hand side of the inequality there.
Yeah, sorry. Yes.
Thank you.
Yes, it is important for this statement. There are variants of these statements that do not require this nor this. But in this case, the only concept of gradient flow that I have is a concept that works well if the initial point has finite energy. So I have to enforce this. Okay? So it is not sufficient that the initial points converge to the initial point. It's not even sufficient that the energies converge. It is important that the energy remains uniformly bounded. Indeed. Okay. Let's prove this. Actually, the proof has basically any proof that involves gamma conversion. The proof is easy. Okay. Here it is. Okay, compactness. Compactness is an exercise. It's Ascoli-Arzelà basically, because what you have. The definition of gradient flow trajectory ensures that the energy, well, let me just say the energy of, say, okay, gamma 0, this is greater or equal if you wish, and the energy of gamma t plus 1/2 integral of gamma t dot squared, it's S, will be R, e, plus the slope squared, right? So in particular, it is greater or equal of this. Now, if you have a sequence of curves for which these guys are uniformly bounded from above, and they are, and these guys are uniformly bounded from below, and they are because the functions are non-negative, then what I have is a sequence of curves for which this integral is uniformly bounded. Okay? But a bound on the kinetic energy gives a bound on quantitative information about Hölder continuity, because the distance between gamma t and gamma s is less or equal than the integral from t to s of the speed, which is less or equal, Cauchy-Schwarz s minus t square root of the integral, let's say, from 0 to capital T of gamma r squared. See what I mean? So if I know that on a big interval, 0 capital T, the energy is finite, on that interval, I have an explicit Hölder continuity estimate for my curve. In other words, if I have a sequence of curves for which I know that this quantity is uniformly bounded, this sequence of curves will be uniformly Hölder. They have value on a compact set, Ascoli-Arzelà, end of the compactness. Okay. What about an limit curve is a gradient flow trajectory? Well, now let me say that gamma and t is converging to some limit curve gamma infinity t, say for every t, right? So what I want to do, I want to pass to the limit in this. Right? Now, this quantity passes to the limit by assumption. This guy converges to E infinity of gamma infinity 0, if you wish, by assumption, this. Right? Or if you wish, the lim sup of this is bounded by this. Okay? These points are converging. The functionals are gamma converging. By the gamma lim-inf inequality, I have that the lim-inf of En gamma nt is greater or equal than E infinity gamma infinity t, just because of this and gamma convergence. Right? So basically, to conclude, I want to prove that I have lower semi-continuity both in here and in here. Right? Now, and these are both easy. And sorry, it's taking a few more minutes, but it's almost done. So we conclude this lecture on gradient flows. And then starting on Monday, we do Sobolev functions. So first of all, so if you want, now I have two sublemmas, if you wish, or observations. If I have a sequence of curves, so gamma nt converging pointwise to gamma infinity t for every t, and I have that gamma nt prime as a function. This is a function, and this converges, say, weakly in L2 to G, in L2, say, I don't know, of some interval, then the limit curve gamma infinity is absolutely continuous, and its metric speed is bounded from above by G of t for almost everything. And the other lemma is that if En, and here convexity plays a role, and this is the crucial point where in this theorem you need convexity. If En gamma converges to E infinity and uniformly K convex, then I have a gamma lim infinite equality for the slopes. Please. All of them are K convex with the same K, not Kn. I mean, K convex if you want. That's okay. So here K convexity plays a role. Notice that this inequality is exactly the one that fails in the silly example I made before about bump. Because if I have bumps and I'm converging to something without bumps, here on the approximated sequence I have point minima, so points, local minima, so points where the slope is 0. But in the limit, the slope is identically 1, so it's not less or equal than the limit. Okay. I mean, these are really. I mean, okay. This is easy because this is remember the representation formula for the slope does the following: that the slope of E under K convexity, the slope of E is the sup, or me say 0 convexity. This is the sup of EX minus EY positive part divided by the distance X and Y. Right. So I say that I want to prove this inequality, knowing that the functionals are gamma converging. What do? I pick an arbitrary point X. I pick a point X and I pick an arbitrary test point Y. Okay. And let me think 1 second. So I should pick the optimal sequence. Which one I should pick? This should be less or equal. I pick an optimal sequence. No? So fix X and Y. X and Y. And Xn converging to X. If I want to prove the limit gamma limit, means that Xn converging to X is given, and now I find Yn recovery sequence. I'm going to Y recovery sequence. So where the functionals converge, and then you see that this guy E of X minus E of Y divided distance between X and Y, this is less or equal than the limit in N of En Xn minus En Yn divided by the distance. Make sense? Because I have lower semi-continuity at this level, and this guy converge. So this is true also if I take the positive part. But of course, for every n, this is bounded from above by the slope of the n at xn. So this is less trivial than the limit of the slopes of En at xn. Right? But now I've done, this was true for any y. So I proved that the slope of the limit guy is bounded from above by the limit of the slopes for any approximated sequence. Okay? So this is trivial. And I leave this as an exercise. So I can conclude the course. Okay, the lecture. So I don't. So perhaps let me just say I will not comment anymore about this statement of this result, except that in many applications this sorry. I think I mentioned this, but I didn't say. So this, so in order to get this compactness, I need the compactness of the space where all these guys belong. Okay, my result and the one of well, my result certainly assumed compactness, Sunday separately probably something a little bit less like compactness of sublevels or something of this sort. I don't remember exactly. But I want to say is that in many applications where you want to pass the limit on CD or RCD spaces, I mean, you might want, and typically, I mean, in many applications, you really want not to have compactness. And the generalization of this result from compact to non-compact case is actually quite tricky and requires a deep understanding of, well, I don't know the generalization of this result, but I can apply this to the heat flow. So to pass the limit on heat flow on convergent sequence of CDK infinity spaces. But if I don't assume compactness, more work is needed. And the generalization to the non-compact case of the heat flow convergence has been done by myself together with Mondino and Savare. I wanted to mention this because on the other hand, the generalization to non-compact case of stability of the CDK infinity